All right, number 7, we have a formula for the volume of a cone. It says water is being pumped in at a rate of 200 cubic inches per second. So that's the change in volume with respect to change in time. 200 cubic inches per second. Okay? And the height of the water is always 3 times the length of the radius. So height is always 3r. Okay? Find the rate of change of the radius. So we're trying to find change of the radius is dr dt. That's what we're trying to get at. When height is 6. So that's something we were given. Now, right away, we could say, well, if height is 6, then the radius must be 2. So that's something that we could figure out kind of right away. But obviously, we're going to have to take this initial equation. We're going to have to do a derivative on it and use that. Now, since we're asking for the change in radius, and we know how the radius is at this point based on the height, what we can do is something slick first and would help us out quite a bit. And that is, let's not have multiple variables if we can help it. Let's try to get rid of one if it's possible. Since we know that the height is always 3 times the radius, let's put 3r in for h right there. And so we get an equation, volume equals 1/3 times pi times radius squared times 3r. And what's nice about this is the 3 and the 1/3 will cancel, and r squared times r becomes r cubed. So for this particular cone that we're talking about, its volume is pi times the radius cubed. And now when you take the derivative of that, you get 3 pi r squared, bring the 3 down, drop it down to a 2, times dr dt. All right, so now we want to know what was going on. How is the rate of the radius changing when the height is 6? When the height is 6, the radius is 2. So we're going to put 2 in there. And we know the volume is changing at a rate of 200. So I'm putting 200 in for the change in volume. 3 pi times radius, which we said is 2 squared, times dr dt. So if I do this, this is 4. 4 times 3 is 12. This becomes 12 pi here. All right, and then we can divide by 12 pi. So the change in radius with respect to time is 200 over 12 pi. And if you do that, make sure you put the 12 pi in parentheses. It would be easy for you to forget and just go divide by 12 and think it meant the pi on the bottom, but it would actually multiply by pi. Should end up with 5.305. And change in radius, change in time, we're talking about cubic inches. So this will be inches per second. That's how fast the radius is changing in that moment. All right, so we had, this was the key, like plugging that in is not obvious, and that's what's so helpful in this problem. And if you don't do that, then it becomes a lot harder. It's still possible, but it becomes a lot harder. All right, find the slope of the line tangent. So we've got another implicit differentiation here, and this is a product rule. So I'm going to take the derivative of the first, which is -1 times y squared as is, plus, now leave the first alone, 4 minus x, times the derivative of the second, which is 2y times dy dx, equals the derivative of there, which is 3x squared. Okay. Now we're trying to find that dy dx. That's our slope of the tangent. So what I'm going to do is that rather than try to get it by itself and then plug 2 in, I think it's a nice idea just to plug this in right away. Let's put 2 in for y and 2 in for x right now. So I'm going to get -1 times 2 squared. That's going to be -4 plus 4 minus 2, which is 2, times 2 times 2 times dy dx equals 3 times 2 squared, which is 4. So if we do that, it's -4 plus 8 dy dx equals 12. Now if I add 4, 8 dy dx equals 16, and then divide by 8, and the slope of our tangent line is 2. So you can get dy dx by itself first if you want, and then plug it in. You'll still get the same answer, but I think in this context it's a little easier just to plug the point in and go. All right, now we get our last one, which is a ladder leaning up against a wall. It's a nice idea to kind of have a visual on this. So here's our 10-foot ladder, okay, leaning up against the wall. The top of the ladder is x feet above the ground. So they're going to say x is the distance from above the ground. and we're base of the ladder is pulled away from the wall at a rate of 2 feet per second. So this is coming off at 2 feet per second. Okay, so that's the information we're told initially. A says find the rate at which x changes when the base is 5 feet from the wall. So if this is 5 feet, okay, so we'll kind of redraw this here for us. Okay, at the moment that this is 5 feet and being pulled away at 2 feet per second, what is dx dt? That's what we're trying to figure out. So we need a relationship between the three sides, and that's Pythagorean theorem, right? X squared plus y, we'll call this value down here, we'll call it y. Y squared equals our ladder squared. Now our ladder is a constant 10, so we don't want a variable there. It's not changing, it's always 10, right? So that's that. Now if we take the derivative of this, we're going to get 2x times dx dt plus 2y times dy dt